So shall we start the session?
Yes, we can.
Okay. A very good morning to one and all present in the online 5-day faculty development program on recent advances in forensic analysis in civil engineering, which is sponsored by AICT Training and Learning ATAL Academy during 27 September to 1st October 2021. So before starting the session for the participants, there are some important points that the participants are requested to keep their mics off during the session, and they can send the queries, if any, on the chat box, and at the end of the section you can unmute your mic and you can ask the questions. So now we are going to start our session 7 on seismic vulnerability assessment of structures by Professor Hemant V. Kaushik. So now I would like to take the privilege to introduce our guest. Hemant V. Kaushik is a professor in the Department of Civil Engineering and head of Center for Education Technology at Indian Institute of Technology, Guwahati. He is present principal coordinator for the Quality Improvement Program QIP of All India Council for Technical Education AICTE. He received his PhD degree in civil engineering from Indian Institute of Technology IIT Kanpur. He is active academically and professionally in the area of earthquake resistance design, nonlinear behavior, seismic retrofitting, large-scale testing, vernacular housing typologies, and earthquake damage surveys. He received the Young Engineer Award from the Indian National Academy of Engineering INAE in 2010 for his contribution to the earthquake structural engineering, and later he is selected as INAE Young Associate in 2013. Professor Kaushik is a member of the Earthquake Engineering Sessional Committee CD39, Bureau of Indian Standards, that looks into the development of standard course of practice of earthquake resistance. He is a member of several international and national professional societies and institutes. He has published several research papers in national and international journals and conferences on different research areas and has received national and international awards for some of his excellent publications. So not taking much time, I would like to Professor Hemant V. Kaushik sir to please start the session. Over to you, sir.
Yeah, thank you, Madhusha. Thanks for inviting me. Let me share the screen.
Yes, sir.
And to reduce the bandwidth, I'll stop my video. Is that okay?
Yes, sir. Yes, sir. Yes,
I hope you are seeing it.
yes, sir. It is visible.
Okay. So today's presentation is about seismic vulnerability assessment of structures. So as the name suggests, we will be discussing some methodologies related to assessment of the risk to the structures, primarily the civil engineering structures, and how to go about estimating or assessing the risk, considering all the uncertainties, considering the different available programming methods, considering available material conditions with us, the construction scenario in India, and many other parameters. So this is primarily a probabilistic methodology where you will find that there are many mathematical terms, many formula that are required, that are essential to assess the vulnerability. But I will try to reduce all those mathematical terms as far as possible and discuss more in a practical sense rather than only the theoretical sense. So first, let us discuss what is the need for assessment of the seismic vulnerability and why specifically the seismic vulnerability. The reason is when we design our structures, we are very good at designing the structures for the gravity loads, even though the gravity loads themselves are not deterministic. We have some methodologies available using which people actually determine the dead loads and live loads on the structure, that is also probabilistic. But then we have pretty good understanding on the kind of uncertainties associated with that. So we are good at designing our buildings for gravity loads. As far as the earthquake loads are concerned, there are certain issues till now. We have not been able to do that. We not in the sense only in India, but I'm talking about the world over. There are many issues which are still to be addressed as far as the earthquake resistant design is concerned. So if you look at the two different loading conditions, first is the gravity load, the vertical load that we always design our buildings for. And the second is the lateral horizontal earthquake loads. So what is the difference in the behavior of the structures considering these two different loading scenarios? In gravity loads, we understand very clearly that if there is a load acting on this beam will behave or will deform like this. And because of this deformation, there will be such kind of deformation in columns. So we know very clearly in very deterministic sense that there is always stretching of the members here at the bottom of the beam in midspan and at top of the beam near the supports. So these are the locations where we need the reinforcement. Similarly, in the columns, we know very well that where will be the tension, where will we need the steel more. In case of earthquake loading, the first is the earthquake loads the reverses. They reverse. So they change the directions at every instant of time. So at one instant, it will be acting from left to right for this frame, at the other instance from right to left. Now, because of this change in the directions, the bending of the members, it also change. So for one particular instance, the face of the member or the location in the member that is under tension, that may not remain under tension at the other instant, or some other locations in the members, they will undergo tension. So that means we need to provide, we need to be careful about designing these members as far as the earthquake loads are concerned. Now, because of this change in the deformations, there will be change in the bending moment diagrams, there will be change in the shear force diagram, all other force resultant quantities, they will change. But for gravity load, this diagram remains the same. So that is why we are good at designing our structures for this loading, for the vertical gravity load, and we have been doing it since several decades. Here, in case of earthquake load, again, you see the bending moment diagram, the signs of the bending moments, they change when the when the direction of the earthquake loading reverses. So clearly, we have to provide the reinforcement on both the faces. It's completely different than what is there in case of the gravity load. Now remember, here I'm not applying the gravity load, but earthquake loads are also associated with the gravity loads. So this bending moment diagram will be slightly different than what you're seeing here. This is only for the earthquake load. This is a simple change in the behavior of the structure when these two different types of loads, they act. There are many other uncertainties related to this type of loading. We will discuss all those uncertainties. We'll also discuss how to handle, how to take care of these uncertainties in our analysis and design. And finally, how to estimate the vulnerability or the risk. This vulnerability assessment cannot be done using hand calculations. You need to have some computer programs, some analysis tools. So what do we expect from a computer? So we have a structure and we have a computer. So what we want is somehow to feed the structure into the computer, and then we expect the computer to do this analysis and give us the deflected shapes or the mode shapes, which we have just seen. And depending on that, they will tell us the force resultants. We use these force resultants and deflected shapes, mode shapes, to design the structure. Now, this is very simple when I say, but then you also understand that the quality of these deflected shapes, mode shapes, and the force resultants, it depends on the quality of the input. So if you feed junk into the computer, you will of course get the junk out. So the input parameters that we always give, that we give to the computer program, these are really important, most important things to provide realistic input parameters, to model the structure properly so that we get these response quantities. The question remains, like, how do we analyze? So historically, we have several methods of structural analysis, starting with the linear static analysis, which is the most simplest method. And one of the linear static analysis methods is the equivalent static analysis, which is also given in our Indian standards. The next type of analysis, which is slightly more complicated, which requires more input parameters, is the linear dynamic analysis. So as the name suggests, this second method, it includes the time variation. So it is a dynamic analysis. So loads here, they change with respect to time, but this was the static analysis. So in case of linear dynamic analysis, we have quite a few number of methods. So I'm just showing you two here: response spectrum analysis and the time history analysis, where we apply the ground motions, the real ground motions, to the structure, but we assume that the structure is behaving linearly. So there is no non-linearity model here, right? So this is the next step. So here the structure was linear, the loads were static, constant. Now the structure remains linear, but we have changed the loads to dynamic. The third type of analysis is where we consider the non-linearity in the structure. So it may be material non-linearity, it may be geometric non-linearity. So again, we do not consider the variation in the loads with respect to time. So it becomes non-linear static analysis. This is one of the most common methods that people use for fragility or the vulnerability assessment because of certain reasons that we will discuss later. The most complex analysis is where we consider the non-linearity in the structure, as well as we consider the loads to be dynamic in nature, right? So it requires a lot of time, a lot of effort. It's really complex. So we need to have huge number of input parameters obtained properly, realistically. Only then we'll be able to justify the results obtained. These are primarily four methods. And as you go from top to bottom, the time required to do the analysis, the effort required, and the difficulty level, it increases drastically. So like I said, nonlinear dynamic analysis, first you need to identify what type of nonlinearity you have to give to the structure, and then you have to give all the relevant input parameters to the computer program such that it understands that this is the way the structure will behave in a nonlinear manner. Also, it requires the dynamic loading. So this is basically we use the real ground motions here in the analysis. So when we use these real ground motions, these are cyclic in nature, these are actually random in nature. And when we use the material nonlinearity, so a combination of them requires a huge time, effort, and difficulty. So sometimes even a small single frame, it takes hours and hours to complete the analysis. And you can think that a small building, even a small building, will take a few days to get the analysis complete. Now, here you will find that I have not written which is the most accurate method or which is the most approximate method, because it depends on the input parameters. It depends on how comfortable are we with these analysis methods. In several instances, in fact, I will say in most of the instances, when we carry out nonlinear dynamic analysis first, it will give you incorrect results. So what we always do, we always carry out linear static analysis first, and we get ourselves comfortable with the results. And then slowly we increase the complexity. Finally, if you want, you can carry out the nonlinear dynamic analysis, but then with some comfort level. The behavior of buildings during earthquakes is a function of several parameters. So this picture here, it shows 5 different types of buildings which are classified with as far as only the height variation is concerned. So it is very clear here that if you have a very smaller building, very shorter building, then the behavior of this building will be completely different than if you have a higher building, a taller structure, and which is obvious. So the behavior depends on the soil conditions at the bottom, the dimensions of the building, the configuration of the building, and many other parameters. Mode shapes of the buildings are one such are some of these important property of the structure that depends on all these parameters. So whenever we carry out any dynamic analysis, we always first see the mode shapes. That will tell us if there is any problem with the model, how is our structure, what kind of natural frequency is it has, what kind of different mode shapes it has. So it will tell us all those properties. So mode shapes are really important property of the structure. It depends on all the input parameters that we just spoke about. So considering this, considering all these issues, when we want to estimate the risk, we need to know the hazard at a given site. What is hazard? We'll discuss in detail what is hazard and how do we estimate the hazard. We need to know what is the vulnerability of the construction. So that is where today's lecture is all about. Why do we need seismic vulnerability? Because it is one of the input parameters that is required to estimate the seismic risk. That is a simple reason. The risk is also a function of the exposure of the elements. So these 3 quantities, which themselves are quite complex in nature, they club together and then they give the estimation of the risk. Why do we need the risk? In order to develop an integrated disaster and risk management system for any city, any town, we have to understand how much is the risk to different properties, to different things. In order to reduce the social and economic consequences of any hazard, earthquake is just one hazard. If we are living in a flood-prone area, then we need to estimate the risk related to the flood. If you are living in some area where you have cyclones, then you have to estimate that risk. So risk is always a function of these 3 parameters. So hazard changes from region to region, the vulnerability of construction, it changes, and the exposure of the elements, it also changes. So this is why we need the assessment of the seismic vulnerability, primarily to estimate the risk involved. Now, if I want to define the vulnerability properly, then you just concentrate on how many things are required actually to define or to estimate the vulnerability. The degree of loss or the probability of loss to a given element at risk resulting from a given hazard in a specified time, right? So this is a proper definition of vulnerability. So what we are talking about is the amount of loss or the degree of loss or the probability of loss to a given element at risk. So that means maybe we are talking about some elements of a building or the building itself or a group of buildings or a town itself. So this is the degree of loss to the given element at risk resulting from a given hazard. So maybe we are talking about earthquake hazard, or maybe we are talking about the cyclone hazard, flood hazard, or any other hazard in a specified time. So we have to define the time during which we are actually determining or estimating the seismic vulnerability. So we have to determine or estimate all these parameters in order to find the vulnerability. So this flowchart gives you the basic components which are involved in the vulnerability analysis of structures. So what are these components? First, you always need the hazard. What type of hazard scenario is it? Which hazard we are talking about? So let us talk about the earthquake hazard here, the seismic hazard. So we need the scenario earthquake. We need the actual hazard. So the meaning is, if you are located, if you are estimating the seismic vulnerability in Guwahati, where I am presently, then the hazard here is higher. But if you are assessing the vulnerability in Bhubaneswar, then the seismic hazard there will be less. It depends on the location, because this is a seismically prone area. But if I'm talking about this cyclone, the hazard, then of course the hazard in Bhubaneswar will be much more than the cyclone hazard that we have in Guwahati. So this first thing we have to find out, like which type of hazard is it and how much is the seismic hazard. We have to estimate the seismic hazard or the hazard, whatever is the hazard. Next is we have to assess the seismic performance. So here we need the elements and the exposure conditions. So exposure means what? The buildings located in Guwahati city, they are exposed to seismic hazard. That is the exposure conditions. So which are the elements? What are the exposure conditions? We need them in order to assess the seismic performance for this seismic hazard. Depending on that, we define some damage states. We will discuss in detail what are damage states, but in simpler terms, damage states define the damage to the structure. So when we say that this structure is highly damaged, or this structure is not much damaged, or this is medium damage, so that is what is the damage state of the structure. So the degree of damage we define using some quantitative terms. Then we include the uncertainty. There are several uncertainties related to different parameters, like uncertainties related to the seismic hazard itself, uncertainty related to the structural material, related to the even the structural dimensions, the uncertainty related to loading conditions, the soil conditions, foundations. So there are uncertainties are related to many parameters. So we have to consider all these uncertainties in the analysis, and based on that, once we do the seismic performance assessment, we include these, and then we assess the seismic fragility. Okay, depending on the structure under consideration. So here there are different terms which we will discuss, each one of them. So discrete probability method, the fragility curve, etc. So that we'll discuss. Once we have the fragility, we combine this fragility with the damage, probabilistic damage or the loss, to finally get the seismic vulnerability in terms of vulnerability functions. And then we include the exposure time. We overlap the exposure time over this to get the seismic risk assessment. Okay, so now you can imagine here that we have done all of these, right? Including everything, we finally get the seismic risk. Or you can say the seismic vulnerability. So let us consider each of these, let us discuss each of these steps in a more detail. So these 5 steps will provide all the necessary tools to estimate the seismic vulnerability. So I'll devote some of the time in each of these steps that is finally required to find out the seismic risk. First is seismic hazard. So let us discuss how do we estimate seismic hazard and what is actually the seismic hazard. So if you want to define it, it is any physical phenomena, maybe ground shaking, ground failure, associated with an earthquake that may adversely affect human activities. This was a definition provided by Shah in 1984. So there are many other definitions, but in simpler terms, any physical phenomenon associated with earthquake that can damage the structure or it affects the human lives. That is the seismic hazard, because it is related to earthquakes, so we call it seismic hazard. But remember, it may not be directly because of the earthquake shaking, but it may be the effects of that earthquake shaking, like the ground failure or the landslides. There are two methods to estimate the seismic hazard, to do the seismic hazard analysis: deterministic method or the probabilistic method. Choice of the method, whether we want to do the deterministic assessment or the probabilistic assessment, it depends on the scope of the work, the purpose of the work, and the most importantly is the availability of the data. Any probabilistic method of analysis requires huge amount of data, and even deterministic analysis, if you have higher data, more data, then your results will be much better. So these two figures here, they show in summary the method of the deterministic seismic hazard assessment and the probabilistic seismic hazard assessment. So I'll just discuss in very brief what are these. So in deterministic method, we identify the seismic source. So here you can see that these are the two faults where we expect that earthquakes can occur. So, and this is the structure under consideration. So what we find out is the distances are from the source to the faults, and then we fix the magnitudes M. So this is the selection of the control earthquake. So there may be multiple sources of the earthquakes, right? So we have to find out somehow which is the controlling earthquake, which is the critical earthquake for this structure which is situated here. Once we can do that, then the next step is the ground motion selection. So we can plot a curve of acceleration versus distance. So you can see here the magnitude, the data of different earthquakes. So as you go away from the earthquake, the maximum acceleration of that earthquake reduces, even if the magnitude remains the same. So particular magnitude earthquake, you select the control earthquake from here, and for that you develop such a data. Then finally, the site hazard can be estimated using the maximum fixed acceleration, because we know what is the distance, and at that distance, what is the acceleration, maximum acceleration. So this is what is determined: maximum fixed acceleration or other measures characterizing the ground movement. So this is deterministic. It will simply say that if this is the distance of the structure from the source, then this is the maximum acceleration for which you need to design the structure for. Deterministic. In probabilistic, the first step is again identifying the sources. So we have multiple sources. The next step here is not fixing the distance and fixing the magnitude, but developing the recurrence relationship. So here what we do, we consider large number of earthquakes that these faults are capable of creating. And we plot the relationship of these magnitudes of the earthquakes and the magnitude and the case where number of cases where the magnitude will be more than that magnitude M, any particular magnitude M. And we plot this recurrence relationship. So we know that if the magnitude of the earthquake is very large, so in the sense that if it is a very big earthquake, 7 magnitude or 7.5 magnitude, the number of such earthquakes will be very less. That we all know. For smaller magnitude earthquakes, the number will be much large, right? So this is this relationship, the recurrence relationship, that tells us what is the distribution of these earthquake magnitudes in that region. Now, based on that, we define the uncertainties in different magnitudes. We plot all these uncertainties in the different magnitude earthquakes, and we plot the peak acceleration versus distance curve. So here you will not get a particular maximum acceleration at a distance, but you get the whole curve. So with changing distance, you get the whole curve with the uncertainty. So if you're considering this earthquake of this magnitude M1, then this is the peak acceleration variation with this much uncertainty. You change the earthquake and you get a different curve. For a different earthquake, another curve. And finally, we find out how much is the probability of accidents of a particular ground motion parameter, right? So this curve will give you that probability that you consider this magnitude, let us say M2 or any other ground motion parameter. It may be magnitude, it may be ground, the peak ground acceleration or the spectral acceleration. And we find out the probability of its accidents. So acceleration of 0.2 g, how much is the probability of accidents? So this curves gives us that. And this is basically the probabilistic hazard, right? So there's a, let us say there's a 50% chance of accidents of magnitude 6 earthquake, or there's a 25% chance of accidents of 0.3 g PGA, right? So this is how we define the seismic hazard. And what is the kind of output of this seismic hazard analysis? So it is shown here. So before discussing this, let me discuss this curve first, this figure first. So this is the design response spectrum given in our IS code. Using this design response spectrum, we design our structures. So the deterministic response spectra is shown here. So what it gives you is the period of the structure. Let us say it is 1 second. And for that structure, what will be the spectral acceleration? How much will be the design acceleration considering 3 different types of soil? So if the structure is located on rocky soil, then it will be required to be designed for lesser acceleration. If it is on the soft soil, it will be designed for the higher acceleration, the same structure, having one seismic hazard output is being prepared for India. And I think within a few months or a year, we will also get such kind of maps in our IS 1893. Okay, so once we determine the seismic hazard, the next step is building typology, determining or the identifying the building typology. But before I go to that slide, let me just ask you if I'm audible to all of you, because I'm speaking alone here.
Yes, sir, you are audible.
Okay, thank you. These online classes, we don't know if you are disconnected or you are speaking alone. Okay. So let us discuss about the building typologies, because once we define the seismic hazard, we have to actually look for the exposure conditions. We have to find out what type of building typologies are existing in that zone, in that city where you are interested in determining the seismic vulnerability. This is very important step because particularly in Indian conditions, you will appreciate that there are large number of building typologies available here. So unless we know what type of buildings are there, we will not be able to determine their performance. We will not be able to then determine how will they damage under different seismic hazard conditions. So then it's impossible to assess the seismic vulnerability. So let us see, how do we identify these building typologies? Now, the simple step here is identifying a step of identifying the building inventory is to first know what are the sample of buildings. We cannot visit every building in a city to do this, but we have to which represent the prevalent building stock in an area. Now, there are large number of parameters that are considered in classifying the buildings. And some of these parameters, they are the structural material, reinforced concrete, steel, masonry, aluminium, whatever. Structural system and configuration. So is it a frame system or it is simply an unreinforced masonry building? The configuration means whether it is a open ground story building or it is a braced building or it is a very tall building or short building. So that comes under configuration. The number of stories or height, low rise, medium rise, high rise, the age of the building, how is the maintenance, because the buildings maintained poorly will of course perform poorly during earthquakes. So, and this is not easy task to find out. What type of soil is there? What type of foundation is provided? Is there a structural continuity or there are structural gaps between different modules of the structure? What type of design and detailing is there? What is the construction quality? Now, this is again a very complex quantity to determine for older structures. You don't know what type of quality was there 20, 30 years before when the building was constructed. And proximity to other structures. So sometimes what happens that the building under consideration is really good, but then the adjacent building is poor. So the damage to the adjacent building may lead to damage to the building under consideration. So there are many documents available, actually large number of documents available. There are two very widely used documents. The first is the PAGER, Prompt Assessment of Global Earthquake Response. And second is GEM, so Global Earthquake Model. So these are widely used models to define the building inventory. And you may not appreciate now that why we need to be so much worried about this building inventory, but in 2-3 slides you will start appreciating it. Now, there are many models available in the literature which define these building inventories. For example, the Medvedev and Sponhier, they define the MSK classification. So they're more worried about the construction material, right? They don't bother about the building height. They don't bother about the load resisting system. Only based on the construction material, they define the building inventory. But then there are many others. For example, ATC 13, it defines everything. It identifies or classifies the building based on load resisting system, based on building height, based on material, based on construction quality, soil foundation, age, proximity. So it's a very detailed document. Similarly, you have many other, right? And this MSK, you must be knowing that it is the intensity scale, same intensity scale. Another is EMS, that is also used. FEMA documents are there. Recently, this HAS-US, or people also call it HESUS. This is one of the most recent and one of the most detailed building inventory documents. So you will find large number of buildings in the whole world here. Then many others like European project, major classification comes here. This is the global earthquake model, GEM taxonomy. So it is also very detailed. Once we understand what type of building typology is there, then the next step is to determine its seismic performance, to model this building and find out how this building is going to behave or perform during earthquakes of different intensities. Now, if we don't know the type of building, if we do not know what type of material was there in the building, what type of framing system is there, what are the dimensions, proper dimensions, what are the lateral load resisting elements in the building. If you don't know these parameters, it is impossible to find out the seismic performance. We cannot plot the bending moment diagrams. We cannot model the nonlinearity in the building. So that is why it is very important. I was involved in one of these studies where we find out how many building typologies exist in the northeastern part of India. So in all the states here. So we visited many places and we found out that in a single Arunachal Pradesh state, there are more than 500 building typologies. So you go to different village, there are many building typologies which are not there in any other village. Similarly, if you cover the entire country, you will have thousands and thousands of building typologies. And these building typologies, they change the configuration over a period of time. So one simple example is even in reinforced concrete buildings, we sometimes remove some wall or we sometimes add some wall somewhere based on the necessity. So this changes the type of the building. It changes the behavior of the building during earthquake, right? Because you are changing the stiffness of the building, you are changing the mass of the building, changing mass in the sense the location of the mass in the building changing. So that changes the behavior of the building during earthquakes. Fine. So next is the seismic performance assessment methods. Once we define the hazard, once we define the building typology, so we understand the hazard, we understand the type of building. Clubbing these, we have to find out how this building will behave during earthquake. Now, there are primarily two methods that people generally use in seismic performance assessment. These are nonlinear static method and the nonlinear dynamic method. Both are good, both have their advantages, both have their disadvantages. So depending on the availability of the data, depending on the requirement, we use them, both of them. Nonlinear static and nonlinear dynamic, as the name suggests, both will cover the nonlinearity in the material or the nonlinearity related to the geometry. But in the first case, here the loads are static in nature. So we don't use the ground motions here. In the second case, the loads are dynamic in nature. So we use the real ground motions for structural analysis. And that is the whole reason that the nonlinear static analysis methods are computationally less extensive. So they require less computational time and effort. But nonlinear dynamic methods, because they need the real ground motions, they are comparatively high they require higher computational time and effort. We cannot include the higher mode effects or the dynamic effects here, the inertial effects here. We include them, but within approximation. But the real inertial effects cannot be included like we include in dynamic method. The hysteretic characteristics, so basically the cyclic nature of the loading with high frequency, that is not determined here in case of nonlinear static. But in nonlinear dynamic, we can do all these things. But we require a lot of more input data. So We will first start with very simple method, which is the capacity spectrum method of analysis. So what we do here, I mean, first, why do we need this capacity spectrum method? Is to basically determine what will be the performance of the structure because of a particular earthquake. Okay, so there are two different modules here. First is the construction of demand spectrum. How much is the demand on the structure? And the second is construction of the capacity spectrum. So how much is the capacity of the structure? So we need to combine these two. We need to superimpose the demand and the capacity of the structure to get how much will be the requirement from the structure from that particular hazard. So you know, how do we calculate the demand? We have already covered the seismic hazard assessment. So it's basically we consider the earthquake, and from that earthquake record, we develop the demand spectrum, the spectral acceleration versus the spectral displacement. So this is ADRS spectrum. And we convert this elastic design spectrum, elastic demand spectrum, to the reduced demand spectrum, considering the various uncertainties, considering variety of parameters. We'll discuss this later. So once this is ready, then we come to the analysis of the structure. So here we are modeling the structural system. We are applying the loading. This is a simplistic modeling for nonlinear static analysis. And we determine a curve which is called the pushover curve. So what it gives us is how much loading we are applying. So the resultant base shear, the resultant lateral force applied at the base of the structure because of this loading, we plot it with the displacement of the structure at the top. So this curve gives you that. Now it is naturally when you apply smaller displacement or when you apply smaller base shear, the behavior of the structure will be linear, but slowly there will be non-linearity, and it will achieve the strength, and then it will start degrading, and finally it will fail. Now, in order to achieve this, we have to define a lot of parameters here. We have to tell the software how each of these members will behave in a nonlinear manner. What it should do, what the software should do if a particular member fails here. So everything we have to actually specify to the software. Now, once we get this, we convert this base shear displacement pushover curve to again the capacity spectrum, like the demand spectrum. So there are bilinear idealization methods. So that is what is shown here. So once we get these two, we have to club them. We have to superimpose the demand on the capacity, and then we can find out that this is the performance point of the structure. So like I said, the intersection of the pushover curve and the reduced demand spectrum, both in the ADRS format, gives you the performance point. Okay. So what do you mean by this performance point? So this figure shows here the performance point. So this blue curve is the capacity spectrum that is coming from the structural analysis, nonlinear structural analysis. And these red curves, they are the response spectrum, elastic response spectrum. We reduce this elastic response spectrum for different damping conditions. And it's an iterative method. So this point here, which is the intersection between the demand spectrum and the capacity spectrum. So the coordinates of these points, they will give you the acceleration that the structure will be subjected to and the displacement that the structure will undergo if we apply this type of demand. So this demand is corresponding to a particular earthquake. Okay, so this is what we need actually, API and DPI. So there are many input parameters here which are required to do this. It is not a simple task, but then to our benefit, software does it automatically. most of the software, they do it automatically. So require many things related to damping, related to the building type. So for example, this we are doing for building type C as per the ATC 40 method. So for different building types, you can get different types of. Okay. Another method is the displacement coefficient method. So here we don't require the conversion of the capacity curve into a capacity spectrum. So if you remember here, we converted this capacity curve into this capacity spectrum, which is SA versus SD curve. Again, similar to the demand spectrum. Only then you can superimpose these two. Okay, so that it takes time to do that. So therefore, the capacity spectrum method that is shown here was modified, and people have proposed another method, which is displacement coefficient method. So the steps are similar. We first construct the bilinear capacity curve, and we calculate the effective fundamental period from the bilinear capacity curve. So we calculate the target displacement, and there is a detailed methodology given where, without converting the capacity curve into capacity spectrum, we can determine the target displacement using this method. So what we need is actually the target displacement so that we can move to the next step. Then there are other methods also available. For example, the N2 method is there for seismic performance assessment. It is based on the ductility dependent inelastic response spectrum. If you remember, previously we used the elastic response spectrum on equivalent nonlinear response spectra. So here is the inelastic response spectrum. It is a non-iterative method. You don't have to do multiple times. It directly gives you the displacement, the target displacement. So the steps are given here. You determine the elastic response spectrum in ADRS format. Then you obtain the base shear roof displacement relationship, like we already discussed for the multi-degree of freedom system. And then we transform those to, again, FD curves using the transformation factors which are generally given. Now this relationship is then again converted to the elastoplastic force deformation relationship and then to ADRS format. Again, we need this capacity diagram like we used in capacity spectrum method. Now determination of this inelastic demand curve, basically the response spectrum, is done using these methods, which are standard methods available in any book. So once you do this, we are ready to determine this gives us directly, without iteration, the target output. So this is as far as the nonlinear static analysis methods were concerned. Now there are nonlinear time history analysis. So these are the dynamic analysis where we consider the nonlinearity of the structure, as well as we consider the real ground motions, which are random in nature, so the loading here is a function of time. So what we do here is we apply the acceleration record data to the structure and we obtain step-by-step response of the structure. So you will realize that here the output that we get is very large. Huge amount of output is generated here. So let us say you have an earthquake which is of 30 seconds duration. Now you have to define these earthquakes using large number of points and you give it to the software. So for each of these points, for each of these accelerations in the response, in the ground motion record, the structure will respond. And for every instant, you get a response of the structure as an output. So it's the overall the size of the output is tremendous here. So you have to read it. It's very complex, and how to interpret the output. So the dynamic equation to be solved is very similar to what we have already studied in structural dynamics. So this is all done in the software. We don't have to worry about how to solve this equation, because it is not for a one instant, for a single instant, but it is for thousands of instances. So we cannot do it manually. Now, people have actually then devised additional methods to get additional data. For example, one such method is incremental dynamic analysis. So here what we do, we perform a series of dynamic analysis, nonlinear dynamic analysis. So not for one ground motion, but for large number of ground motions. And people not even use one ground motion once, but they change the intensity of the ground motion. They change the acceleration of the ground motion, single ground motion, to let us say 10 different peak ground acceleration or 20 different peak ground acceleration. And then they start doing hundreds and thousands of analysis to get response of the structure with varying ground motions. So that gives us incremental dynamic analysis. So we start with a very small earthquake, and then we keep on changing or increasing the intensity of the earthquake and find out how is the building behaving. So it is written the series of nonlinear dynamic time history analysis in which the intensity of the selected earthquake monotonically increased until the global collapse of the structure. Now, again, it is not easy to find out when the structure is collapsing, because it is not something which is similar to the nonlinear pushover analysis. Here you have to actually plot the IDA curve, and depending on the slope of that IDA curve, IDA means incremental dynamic analysis. Depending on the slope of the IDA curve, you have to judge, like, this is where the structure has yielded, this is where the structure has collapsed. But it gives you a lot of additional data. Fine, so once we know somehow how is the seismic performance of the structure, the next step is integrating the damage, integrating the uncertainty, and integrating the fragility to this seismic performances. The first step is the damage states. We have to define these damage states to a particular structure. To see these damage states, again, they are a function of, they will be different for different building typology. Okay, so for reinforced concrete buildings, the damage states will be different. For unreinforced masonry buildings, the damage states will be different. So you have to define them for different types of buildings. The states of damage can be quantified in the capacity curve. So if you remember, this curve here is the capacity curve, right? And this red curve here is the demand curve, which is coming from the response spectrum. And this capacity curve, we have already discussed, it is coming from the analysis method. So maybe pushover analysis or maybe the dynamic analysis. So we can quantify the state of damage in the capacity curve such that each individual stage is shown as a damage state. So if I define some damage state where, if I want to define a damage state such that the structure is not at all damaged, no damage at all. So obviously that will correspond to the stage of the structure before it reaches the nonlinearity, right? So here the structure was behaving linear in nature, right? So here is the nonlinearity in the structure. So before that, there is no damage at all. So this becomes the non-damage state. So after this nonlinearity, there will be slight damage in the structure. So we can define that if this SDY is the spectral displacement at yield. So you can define that up to 0.7 SDY, there is no damage. So this is a non-damage state. From 0.7 SDY to about 1.5 times SDY. This is the zone in which there will be slight damage. So the damage state is slight here. Similarly, the moderate damage from 1.5 SDY to 0.5 SDY plus SDU. Now this SDU is this displacement at which SDU means the ultimate spectral displacement, after which the structure starts degrading the strength. So this becomes the moderate damage state. The extensive damage state may be between these 2 points, may be defined between these 2 points. And then the complete damage state is beyond SDU. So this is how we define the damage state. So there are many damage state scales available in the literature, but it may not be applicable to the user all the time. So there are many cases where people develop their own damage states. They define the damage states properly. So for example, if I want to know from the capacity curve, where is the yielding? Where is the nonlinearity? This curve here is the bilinear representation. So it's very clear from here that here the nonlinearity starts. But in real systems, this is not such a clear demarcation. The nonlinearity is gradual in nature. So there we have to define somehow that here is the point, or I am assuming the nonlinearity where there is a first yielding in the steel bar. So that is easier to determine in the software. Similarly, the collapse, the complete damage state. How will you define SDU? It is not easy. See, the curve will be continuous and it will be nonlinear. So it will start degrading from here. So up to what degradation you will say that it is not complete damage state. So these definitions the user has to create. So one simple definition of collapse or the complete damage state is, for example, I define the complete damage state where at least 25% of the columns in the ground floor of a building have failed, right? So when 25% of the columns in the ground floor fail, to me, that is the collapse of the structure. So that it is not complete, it is not collapse, but it is a complete damage state. But still, people will have time to leave the building, even if 25% of the columns are collapsed. So I define the complete damage state at that point. But depending on the type of building, depending on the age of the building configuration, you can even define that 50% of the columns, if they are remaining, still the building can stand. It will not collapse. So that is the complete damage state, right? So let us say that there are several frames in the building in which there are reinforced concrete shear walls. And there are some frames in which there are columns, no shear walls. So then you can define a different complete damage state. So it depends on building to build. It changes with building to building. It depends on the user. So these damage states I'm showing you here, they are taken from Legumarcino and Guazzini in 2006. And these lines here, they define the threshold. So initial point of each damage state, they are called the thresholds. So this point here is a threshold of complete damage state. This is the threshold of the extensive damage state. Okay. The large number of people, the large number of literature which are available that define the damage state for different types of structures. So starting from 1989, you have based on experience and judgment. So damage states were defined based on colors. So green, yellow, and red. Of course, red is for unsafe. And you might have noticed these kinds of stickers pasted on buildings after the earthquakes. So they come from some ATC guidelines. Then there are many other damage state definitions. So Hayes US has us, it defines 5 damage states. based on structural and non-structural damage for different model building types. So these damage states are none, slight, moderate, severe, and collapse. Then EMS, they define again 5 damage states. So they define in terms of negligible to slight damage, slight to moderate damage, slight structural damage to moderate non-structural damage, right? So people have devised several methods, several definitions to define these damage states. And these are all related to different buildings. And there are many studies actually. So this is the scale, this is the damage state that we discussed, Legomarcino and Giovinazzi. So it depends on the yield displacement and the ultimate displacement of unreinforced masonry building or the reinforced concrete structure. So 4 damage states we discussed. Then Rossetto, they define 7 damage states, right? And then similarly Barbat, they have different damage states. So people have defined a large number of methods. And you can use any one of them, or you can actually define your own damage states. So once we define these damage states, we can now say that this building, how is the performance of this building at this damage state, right? But then we have to consider the uncertainty also. Let us discuss what are the different types of uncertainties, because it is very important to know how approximate our solution is, our assessment is. Now the classification of different sources of uncertainties for fragility curve definition are shown here. So what we generally do is that we consider the total uncertainty as the SRSS of all possible uncertainties. SRSS means square root of sum of squares. So for a particular damage state, this beta I, the different uncertainties, can be a combination of uncertainty in capacity, which is shown here. So the total uncertainty, we can actually classify into 2 types: uncertainty in capacity and uncertainty in demand. There are other classification, but then we'll concentrate only on these 2 because these are major. There can be some other also. Now, uncertainty in capacity means the structural capacity. So of course, all the structural properties will come into picture here. So first is, what is the dispersion in the mechanical properties? Simplest example, if I specify that the grade of concrete in the building is M25. Now you already know that this M25 is a very approximate quantity. You test 6, 7 cubes or 10 concrete cubes in laboratory and you get different results. You plot it and then you get the characteristic strength. It is not the mean strength, right? So the 5% not more than 5% of the specimen should fall beyond that. So we define that FCK in that manner. M25 means this 25 is the FCK, characteristic strength of concrete. What is the error there? There's a huge error, right? So we determine the standard deviation, 1.65 times the standard deviation plus the mean value. That is how we do all these calculations. So now you understand that there is a huge dispersion in the mechanical properties. Similarly, the dispersion in the steel properties, the masonry properties. So all those dispersion, all those uncertainties come here. Then the geometric properties. When we say that the length of this member is 3 meters, it may be 3.05, 3.1 meter or 2.95 meter. So in just one member, right? So considering a big building, it may sometimes lead to erroneous results. So these geometric properties, they'll be having uncertainties. Structural detailing. So the things written on the drawings may be different than the real things that are provided in the structure. So detailing things. Numerical modeling. This is one of the biggest source of uncertainty. If I give a structure to a group of students and ask them to model a structure, they will model in n number of ways. So everybody will, the structure, everybody's structure will be different. The behavior of the structure will be different because of different assumptions. One simplest example here can be, how do we provide the boundary conditions at the base? Mostly we provide the fixed base condition. We fix the structure at the base, but then the structure is never fixed at the base. So what do we do then? Sometimes we model the soil structure interaction. We model the soil. Okay, but then where are the properties of the soil? So then we have to consider, we have to assume, we have to obtain the properties of the soil. Sometimes we does that accurately. Sometimes there is uncertainty in that also. So this numerical modeling is very uncertain. So combining all these, we get the uncertainty in capacity, which is beta C, and then the uncertainty in demand, beta D, which of course the uncertainty is there in record to record, right? So there are attenuation laws, meaning when the earthquake originates at focus, the earthquake waves, they travel through different soil, through different type of soil, and it reaches the structure, or it reaches the place where the ground motions are being recorded. So how these ground motions change, and then the recorded ground motion at a particular station will be different than the ground motion that are reaching the structures because of different attenuations. So there are uncertainties in them. Every record to record dispersion is always there. So combining all these, we get beta D, beta C, and then we somehow combine them by SRSS to get the total uncertainty in the fragility curve derivation. To simplify this issue, HES-US, they have given some simplistic numbers. For example, for concrete moment frames with and without infill of general type, the values of this log normal standard deviation beta are provided as 0.7 for slight, moderate, and extensive damage state. Okay, for buildings with infill. For complete damage, it is slightly higher. For C3M buildings, so without infill, beta is undefined. Right? For buildings of spatial type, beta values are nearly same or less for the general type. So there are many conditions which are defined in HES, and it says that if you don't have all these data available with you, you can actually consider the overall uncertainty beta, which is actually the log normal standard deviation. That you can consider as 0.7, 0.8 in that range, 0.6 to 0.8. So in our studies, we generally consider 0.7 if we don't have much data available. But then remember, the output changes when we change the uncertainty. Fine, so we combine the damage states with the uncertainties associated, and we finally get the fragility, which is defined mathematically in this manner. So it is the probability of accidents of a particular damage state, right? Which is a function of the spectral displacement and the median value of the spectral displacement at which building reaches a certain threshold of the damage state, DSI, right? So this is the median value of spectral displacement reaching the threshold of damage state. And of course, the beta DSI is the standard deviation of the natural logarithm of spectral displacement. Phi is the standard normal cumulative distribution function. So these values are actually standard values which are given. You can find it anywhere in a normal standard book. So what we finally want to know is what is the probability of accidents of a particular damage state for that structure. So that we define in terms of spectral displacement. Okay. and it represents a continuous relationship between the probabilities of exceeding a particular level of damage state versus any parameter describing the earthquake intensity measure. So it may be pseudospectral acceleration, it may be PGA, it may be spectral acceleration. let us see how we plot it. So this is the seismic fragility in a continuous probabilistic sense. So here we are plotting the probability of accidents of a particular damage state in terms of spectral displacement. And on the x-axis, we have the spectral displacement. So this green curve, it represents the slight damage state. This is blue is the moderate damage state, this is the extensive damage state, and this is the collapse damage state. So obviously, you will find that the probability of exceeding this slight damage state, even at less displacement, will be higher. So the slight damage may occur at a lesser displacement. So that is why the probability is higher there. Probability of occurring the collapse at a smaller damage, at a smaller displacement is very less, and which is shown here. And that is how we interpret these curves. Now we can actually use these curves and determine the discrete probabilities as well. So finding out these relative values, DG0, DG1, DG2, DG3, and DG4, we can plot them here. And we can get the discrete probabilities for individual damage states. I mean, the difference between these two damage states at a particular spectral displacement. Okay, so for 0.07 spectral displacement, you will get the DG0 as this much, 0.05, around 0.04. So this is a discrete probability. Okay, so there are different methods, different ways we can interpret these results. So this damage probability matrix, DPM, it specifies the discrete conditional probability. So this figure here of reaching or exceeding a damage state for a given earthquake intensity. And it is for a particular value of spectral displacement. So for each of the different values of spectral displacement, we can define this probability. Then last is the assessment of vulnerability. Once we have all these, so the vulnerability is of course different from fragility because we have to include the loss estimation also. It may be structural loss, it may be monetary loss, or it may be loss to life, etc. So including the loss to the seismic fragility, we get the vulnerability estimation. Now there are many methods of estimating the seismic vulnerability, broadly categorized into empirical methods, analytical methods, judgmental methods, and hybrid methods. We often use the rapid visual screening, RVS, of the buildings. So if you don't have any of these data available, no hazard, no structural types, no structural capacity, we don't have any idea on all these. So the simplest method, a very preliminary method that people use to assess the seismic vulnerability is using RVS, right? And we can say that this building is safe, it is unsafe in a very simpler sense. But then sometimes, or I'll not say sometimes, most of the times, just by looking at the building, it is impossible to check the condition of the building. So we have to do all these detailed analysis for some buildings. This is how we carry out the rapid visual screening. So we develop the budget, we identify the area to be screened, we review the forms which are required to be filled. When we train the screeners, if it's a large area that is to be covered, we have to involve a lot of people. Then we review the data, we review the building database files and soil types. We review the drawings, construction drawings. Then we screen the building, sketch the plans and elevation of the building. While visiting the building, we have to verify the construction type and the plan irregularities. If access to interior is possible, we take the photographs and we enter the records. So this is a simple RVS which many people carry out. But like I said, it only gives you a very preliminary idea. So it can tell you that only about very good buildings or very bad buildings. So what to do with the intermediate buildings, it cannot tell. Now, next method is the empirical vulnerability assessment, which is based on quantitative or qualitative analysis of post-earthquake damage data. So there are many earthquakes occurring. So people study those earthquake damage data and the distribution of damage. Then they define the empirical vulnerability functions directly from these damage observations from the past earthquakes. And they relate these with the area under consideration. So they can say that if similar earthquakes occur in this area, which is also similar to that area where this earthquake has occurred, so similar types of damage are possible. So based on the limited damage data observed in the field, covering only limited range of earthquake magnitudes, and it's limited to the locality for which the damage data is extracted. Okay, so a region where previously some earthquake has occurred. So for example, there are people who have actually done research and they have given some method of assessment of the seismic vulnerability as the conversion of physical damage into monetary loss given a measure of the ground motion. So it combines this damage, the loss and the ground motion intensity to give some assessment of the seismic vulnerability. Okay, I'll not go into too much detail here, but it depends on, you see, the cost, material cost, the labor cost, and the damage states. So it includes everything. Then it gives you the assessment. The advantage of this analytical vulnerability assessment is that it gives an opportunity to consider multivariate modeling of behavior for real conditions based on detailed numerical analysis. So it combines many things actually. But there are other methods, for example, the judgmental vulnerability assessment. So here a group of people which are experts, they are provided with some forms and then they fill those forms to give us some guidelines on how to estimate the building damage distribution. So this is what they do based on their own experiences in that region. This is this ATC 13 where some of these forms are available. But you see, it is all subjective. It all depends on the person which is doing this assessment. Then the most widely used vulnerability assessment methods are the hybrid vulnerability assessment, which combine the advantages of empirical and analytical methods. So the analytical estimates, they are updated using the empirical studies. So they combine all these. They will take the judgment of the experts. They will also use the methodologies adopted in the past, available in the literature, and it becomes hybrid in nature. Finally, we try to get the risk, which is the natural output of the seismic vulnerability, because that is the whole region of assessing the vulnerability. You can define the risk mathematically, like we have already defined, as a combination of hazard, vulnerability, and exposure. And if you want to define it in a sentence, it is the probability that social or economic consequences of earthquake, losses of lives, injury to the persons, damage to the property, economic activity disruption will equal or exceed specified values at a site. So again, the probability of accidents we are talking about here at several sites or in an area during a specified exposure time. Right? So then similar definitions. Only the time is additionally provided here. So the losses per scenario as a function of annual probability will give the risk curve. So this equation, for example, if you club all these, so for example, Y star is the annual frequency of accidents of design amplitude A here, and Fs is a factor of safety, C is the median structural capacity. KH is the slope of the hazard curve in log space. So there are many variables associated with it. So we need to know the losses. You need to know uh, the time duration for which you're doing this. You need to know the vulnerability, type of structures, many things here. Okay, so combining everything, we have defined the hazard. We have defined the building typology. We obtained the seismic performance. We club this with the damage, uncertainty, and fragility finally to get the vulnerability and the risk. So that is all from my side. Before I close, I'll just show you a very simple photograph with a little interesting story, with a small interesting story here. The photograph, that is this photo here, is a reinforced concrete building. This photo is a wooden building. Photo is of a wooden building, and this is an Assam type housing which is prevalent in this part of the country. This photo here, you can see, this is the wooden building that I'm talking about. So this building and this reinforced concrete building, they are located just across the street. So this is the street, this street, and on the opposite sides of these streets, these two buildings are located. There was a big earthquake and tsunami in 2004, 26 December 2004. Before that, in 2000, I think 2 or 3, this is a government building, PWD building. So people residing or working in this building, they complained that it is a very old building. We don't want to work here. We want ACs in our building. So they constructed this reinforced concrete building right across the road. This building was completed in, I think, 2004, just a year before the earthquake. And then the earthquake struck, the tsunami struck. This building was so damaged, so much damaged, that these people who shifted their offices to this building, they again moved back to this wooden building. They're still working from this wooden building, which is more than 100 years old. Similar is the condition for the Assam type housing. These are being constructed in hundreds and hundreds of years and performing really well. So the point I'm making here is that you can actually assess the seismic vulnerability, do all these calculations, do all the mathematics, find out the assess vulnerability. But then ultimately what matters is the judgment, is the reason to construct the building typology, whether it is feasible there, whether we should construct that type of building, whether we have the material, proper material to construct the building, are we using the proper design and detailing methodology? So all these questions which cannot be quantified really are very important, rather than simply constructing reinforced concrete buildings and then doing all these mathematics. So with this, I thank you all. And if you have any questions, then we can discuss.
Thank you so much, sir. Thank you for your enlightening lecture, and the session was very, very interesting and valuable. So participants, is there any questions? Please unmute yourself and ask. Is there any questions from participants? I think, sir, there is no questions. All the things are clear to everyone.
Great.
Sir, it is an honor for me to invite you to participate in this FDP as expert speaker. And thank you so much, sir, for accepting the invitation. Thanks a lot, sir.
Thank you, Madhusha.
Thank you, sir.
So can I leave the meeting now?
Yes, sir. Yes, sir. You can leave, sir.
Okay. Bye-bye.
So participant, we will meet again at 11:30 am for our next session. Our next session, that is session 8, which will be on stress relief through breath work and meditation by Mr. Syam Agarwal, Senior Art of Living faculty. So all participants are requested to kindly assemble on this virtual platform for the session. So in order to avoid the last minute technical issue, we are requested to join the session before 10 minutes to the session time. Thank you all for your patience of watching, patience of listening, and thank you all. So now you can leave. Again, 11:30 we will meet.